Okay, good morning. Welcome back to the second lecture of Evolutionary Robotics. At the beginning of every lecture, we'll orient ourselves according to the schedule. Today we are going to spend most of the time working our way through a very short history of AI. That could be a course in and of itself. We're going to sort of lay the groundwork for the overall landscape of AI and robotics and where evolutionary robotics sits within that landscape. We did not quite finish the slide deck from lecture one last time, so we'll finish off why robots in a moment. You have a quiz due tonight. I haven't posted it on Brightspace yet. I will do so by about noon today. I will drop the recording of today's lecture also around noon in here. Here's the required reading for today. Undergraduates, you're working on assignment 1, which is due this coming Tuesday by midnight. Grads, you're working on assignments 1 and 2, which are due this coming Tuesday by midnight. Everybody oriented? Disoriented? All good? Okay. All right. So back to lecture 1. We finished last time with some eye candy, sort of visually showing you how an evolutionary robotics experiment works. You create a population of autonomous machines. They are neither safe nor useful because they're random and put together in a random way. The evolutionary algorithm takes over, evaluates every robot in the population, in simulation, deletes those that do a poorer job at whatever it is you want them to do, and makes randomly modified copies of the survivors. Rinse and repeat. Fingers crossed, if you're lucky, you get a machine that becomes increasingly safe, reliably, and hopefully reliable and also useful. That's evolutionary robotics in a nutshell. A little bit more eye candy for you this morning. This is from a very old experiment I ran when I was a grad student. Again, just trying to give you a visual intuition for how an evolutionary robotics experiment proceeds. What is being evolved here? What did we ask the evolutionary algorithm to evolve a robot to do? What is it getting better at over time?
Picking up the block.
Picking up the block. I created a fitness function for my evolutionary algorithm that measures the distance between the center of this blue block and the robot's back. The evolutionary algorithm evaluates a whole bunch of different robot brains. In this case, we're just evolving the robot brains. And it's deleting the ones that fumble or fail to pick up the block and makes randomly modified copies of the survivors that do a little bit better job at grabbing the block and eventually lifting it onto its back. When I put together this video, I did not include all the clips of all the failures, all the fumbles, and all the rest. What you're seeing is a sped up time lapse of this evolutionary process. You're seeing the best or the most fit robot in the population at that point in time in the evolutionary algorithm. So you're seeing the winners, the evolutionary winners, at every moment in time, and you're not seeing all the other losers in the population, some of which are deleted, some which produce less offspring than these. So far, so good? Okay, so that's evolutionary robotics in a nutshell. You're going to be building up an evolutionary robotics experimental platform over the next 10 weeks. What are the 4 main necessary ingredients for such an evolutionary robotics experiment? They are, of course, first of all, the environment. The robot has to operate in some environment. In this class, it's going to be a simulated world. We're going to see a lot of experiments in which we take evolved robots out of their simulated world and deploy them in the real world. So there is everything around the robot. Then there's, of course, the robot itself. What you can't see in this video is the brain of the robot, which in this case is an artificial neural network. Most of you are probably familiar with neural networks from AI and foundation models and large language models. We're going to use neural networks in this class as well, but these neural networks are not going to generate a text response to your prompt. They're going to generate behavior, that in this case, this behavior. Okay, so we need a robot, its brain, the task environment, and finally, we wrap an evolutionary algorithm around these 3 components. For the moment, that's going to be an evolutionary algorithm. Here's the evolutionary algorithm in action. I'm going to show you a second video now, and this is sped up even more. It's the same experiment, but a little bit later in time. What's happening now? What's changed?
Getting a little more coordinated with picking it up.
It's getting a little more coordinated with picking it up, so we can see evolutionary improvement in the behavior of the robot. Yep.
The block is moving away.
The block is moving away. So I set up this experiment that every time the evolutionary algorithm evolves a robot with sufficient fitness, so it manages to actually pick up the block onto its back, I change the robot's task environment, ingredient number 1. I make the environment a little bit more difficult for the robot, and then I just continue the evolutionary algorithm. So what worked before doesn't necessarily work anymore. Evolution has to modify the artificial neural network that's controlling the robot. Yeah. The reason I show this video is it shows some of the pros and cons of using an evolutionary algorithm. What are some of them? What's happening during this evolutionary process? If we took this evolved robot and actually built it in reality, and I sold it to you for use in your home, and you used it to pick up empty soda cans and glasses and fine china, what's the con of evolutionary algorithms? What's problematic here?
Too much computation.
Sorry?
Too much computation.
What do you mean by too much computation?
It takes generations of training to get the right result.
Okay, so this 1-minute video that you're watching took about 2 weeks on UVM supercomputer, which is over in Colchester. It's a huge carbon footprint to produce this video. An evolutionary algorithm has one main drawback, which in AI is called sample inefficiency. It takes lots of samples. In robotics, a sample is running a simulation. It takes millions and millions of failures until you start to get a few successes. So that's one disadvantage. But from your point of view as the consumer, you don't care. What does it matter how much effort I put in to evolve a robot for you? What are some other disadvantages here?
It's only optimizing for the very specific fitness metric you've created.
Yep, it's only evolving. It's only evolving for the fitness metric, which is minimize the distance between the blue block and the little gray ball on its back. So why is that a problem?
It could involve, for the example of picking up glasses, it could just throw it really hard and make it break.
Seems good to me, right? Please put the fine china away in the cupboard, open the cupboard door, and right? It's a huge problem, not just in robotics, but in AI in general. And the formal term for this is perverse instantiation. So when we're training ChatGPT or training a robot, as you see here, we're training it to instantiate some behavior. Put the fine china away, transport the human passenger from point A to point B in a given city. That's the instantiation. If all we do is reward the robot or ChatGPT or the autonomous vehicle for doing what we want, put the china in the cupboard, get the passenger from point A to point B as quickly as possible, things kind of can go wrong. As you can see here, you're actually watching hundreds of different artificial neural networks all taking their turn in controlling this robot. They're all generally doing what we want, which is to get the blue block onto the robot's back. But in some cases, it's doing it in the way we want it to, which is grab the object and bring it onto its back. And in some cases, it's doing it perversely, toss it onto its back. Often, robots and AI are like teenagers. They'll end up doing exactly what we told them to do, but in exactly the opposite way that we wanted them to do it in retrospect after we see how they're doing it. One of the most heartbreaking things as a roboticist or an AI researcher is, no, that's not what I meant. Very tricky. No one has a good answer to this problem yet. It's usually solved with a whole bunch of guardrails and please do what I want and don't do it this way and don't do it this way and don't do it this way and don't do it this way, because we have to keep tacking on all these riders and constraints and limitations in retrospect after we see that the autonomous vehicle's idea about the quickest way to get passenger from point A to point B is a straight line. Yeah? Try and stay off the sidewalks. Yeah? Very tricky. Here's an example of perverse instantiation in robotics. You're going to see plenty of examples of it throughout this course. And when you start evolving robots, you are also going to start to evolve autonomous machines, I guarantee you, that instantiate what you want them to do, but unfortunately, perversely. Okay. There's some more slides here left over about expectations about the course. I'm going to skip over all this. You can just read it. Super boring. Last thing I want to talk about from from the first lecture is the final project. So I mentioned that at the end of 10 weeks, you're going to have 4 weeks more or less to do a final project in this course. You'll see that there's a menu of ideas that we give you. You can pick something from that menu, or you can come up with an idea on your own. If you want to come up with an idea on your own, it can be very difficult to get a sense of what's too ambitious or what's not ambitious enough for 4 weeks, given where you are at the end of the 10th week. So I'm going to show you here a little highlight reel. This is from 5-6 years ago now, of some of the final projects from this course. Sorry, let me start this over again. You're going to see several typical projects that are possible in this class. What you're going to see in the left video is the before, and what you're going to see on the right is the after. The left is that student's robot being controlled by a random artificial neural network. That random neural network takes sensory information from the robot, transforms it randomly into signals that go to the robot's wheels or legs or whatever else it's got. Yeah? So it's basically, what you're going to see on the left is random behavior, and then what you're going to see on the right is evolved behavior. What you're not going to see is, what was the student's fitness function? What did they give the evolutionary algorithm to evolve the robots against? But you should probably be able to figure it out. Here's a random soccer robot. Here's an evolved soccer robot. Perverse instantiation? Maybe, maybe not. It's a little hard to see. There's a little gray cube in the back there. The robot is moving randomly. Might not look like it's moving randomly. Oh, sorry, no, I forgot. This is object carrying. You might not be able to see it in the back. There's a little gray cube. The robot's supposed to walk without dropping the cube. I mentioned fine china before, right? Dealing with fragile objects, very difficult for robots to do. That's a little better. All right, stair climbing, ladder climbing. In this case, the student has designed the body of the robot themselves and then evolved an artificial neural network to do it. Looking pretty good. We're going to be evolving our robots in physics engines. Not all physics engines are perfect. Sometimes there's little bugs in the physics engine itself. Stair climbing, right? You figured this out when you were about 6 months old or a year old, super easy. Turns out it's not so easy for robots. Tricky thing to do stairs, actually. Here's another thing that took most of us a little more than a year to learn. Very difficult. We'll spend a fair bit of time talking about bipedal locomotion a little bit later. Perverse instantiation? Maybe. Maybe not. Here's another attempt at bipedal locomotion. A little bit better. Hand-eye coordination, kind of. Okay. Okay, just to give you a sense of the kinds of things that are possible at the end of the semester. Okay, that's the end of lecture 1. Any questions about that? All good? Okay, so as promised, a very, very, very short history of AI. Like any history, where you start is kind of arbitrary. We're going to start here. When is this? When was this stated? Which century?
I don't know exactly when, but around time of the Romans, because that's Latin, right?
It is Latin. We're not quite going back to Roman times.
I think it's closer to like the Enlightenment era.
Getting closer.
Is it I think therefore I am?
I think, therefore I am in the 1600s. We're going to start with this person who stated this, cogito ergo sum, translated into English, I think, therefore I am. This is a French philosopher from the 1600s who's at this time thinking about what is it possible to know with certainty. Seems like kind of an odd place to start a history of AI. Who is this?
René Descartes.
Thank you, René Descartes. In Discourse on Method, he's thinking about what can I really trust? I see about 50 humans out here, but I know that my visual sense can be fooled. There's optical illusions. Can I be really sure that there's 50 humans out there and 8 or 9 billion of them out there? Can I be sure of this? Can I be sure of this? What can I actually be sure of? So, do I even exist? I don't know. Where does this stop? To René, he started to realize that in this sentence, do I exist, am I real, there's this pronoun I. There is something that seems to be asking the question. Whatever the answer to that question is, yes, no, maybe, who knows, the answer doesn't actually matter so much for Descartes. It was the question itself. There has to be something that's asking the question. So whatever that thing is, which I'm going to refer to as I or me, that thing must exist. Everything else, who knows? Maybe I'm immersed in a pod filled with gel on a farm that's being harvested by autonomous killer robots in the year 2050. Who knows? I can't really know. I can't trust with certainty this or this. But what I can trust is the fact there is this thing called I. For Descartes, for someone living in Western Europe in the 1600s, that I was the soul, right? This immortal thing. So for Descartes, the soul surely exists. I am sure that it exists. Everything else, including my body, I'm not so sure about. Why are we talking about this? Because Descartes cleaved the world in two. There is I, there is self, and there is everything else. Today, depending on who you are, you may be uncomfortable with this world soul, you might be more comfortable with the world mind. Whatever it is, for a lot of folks, there is this thing that's probably in here somewhere, and it's quite different from the body. Mind and body are different. This has become known over the last few centuries as Cartesian dualism, or the mind-body problem. Why is it a problem? There's a mind and there's a body. They're two different things. And by the way, the latter one is not so great. It gets old and gray and starts to deteriorate. But this thing, this kind of seems pretty good for a lot of people. Maybe it survives beyond the end of this thing. Not just are they different, one is kind of better than the other. What's the problem here? There's many problems. Why is it called the mind-body problem?
If the mind is better, but you don't have a body, it can't really do anything.
It can't really do anything. Yeah, what happens when the body goes away? I guess maybe there's this thing called heaven and everything's okay up there, but what does it mean for a mind to exist outside the body? As you mentioned, there's nothing for it to control. And by the way, now that I think about the mind controlling the body, if they're so separate, how? How does the mind, which is maybe not even a physical thing, a material thing, how does it pull the strings of this thing? Where is the interface between these things? Now that I think about it, the interface is even more problematic, or thinking about the interface is now even more problematic than this immaterial mind or soul and this physical thing. Okay, we're not going to go more into the mind-body problem, but this is a very, very deep idea, at least in Western thought. Even for atheists who are scientifically inclined, there's a mind/brain that somehow controls the body and vice versa. They're different. Okay, we're going to see throughout this entire course that cleaving of the world in two, this cleaving of the mind from the body, has actually percolated into the fields of AI and robotics. Hey, wait a second, AI and robotics. In one field, in AI, they're trying to create autonomous machines that don't have a body. Roboticists are trying to create autonomous, useful, and safe machines that do have a body. You can see the Cartesian cut already in the way that we as a society are trying to create autonomous, safe, and useful machines. Some say we can do it with just this thing, and others think we need some combination of these two things. So the reason that we're starting in the 1600s with Descartes is there is a very deep bias in the way that we think about a lot of things, including ourselves, and it influences how we think about other things. Animals, organisms. Do non-human animals have a mind? Do they have a self? Can we create machines that have a mind? Can we create disembodied machines that don't really even have a body? They can just be a mind running inside a computer. If we can create machines that have a mind, do they need a body of their own? All of that way of thinking guides the kinds of questions we ask about our pursuit of intelligent machines. That's why we're starting with Descartes. Okay, we're not going to spend a lot of time in the 1600s. Let's jump ahead exactly 300 years to 1936. The very idea that we could create autonomous, useful, and safe machines came about in a couple of the years before the Second World War, and then in the Second World War, very much people were thinking about complex and autonomous machines. So you could very well argue that AI and robotics were kind of born out of the Second World War. Okay. This is the Turing machine, named after Alan Turing. Hopefully you all know that name. In 1936, he sort of was just thinking about this and had sort of this thought experiment about a hypothetical machine. And this machine had certain properties. This machine was exposed to a tape that you see here. There are separate segments on this tape. And for the computer scientists in the class who have heard of Turing machines before, for the benefit of those who have not heard of Turing machines before, what are the few things that a Turing machine must do? What makes a Turing machine a Turing machine?
Encryption and decryption.
Sorry?
Encryption and decryption.
What do you mean by encryption and decryption?
Like using supercomputers to decrypt the message.
That's something that a Turing machine can do. Like, what kind of problems can it solve? It can decrypt things, which obviously became important in the Second World War. But what basically does it do? Not necessarily what kind of algorithms can it run.
It reads from a tape that has a head that reads one section of the tape at a time.
Excellent.
Move left to right.
Okay, so it can read from the tape. There's the input. You mentioned it can move back and forth. That's kind of its output. Either the machine moves back and forth, or the machine moves the tape back and forth in front of itself. So we have input, read from the tape, and output, move back and forth. There's a couple other things that a Turing machine is capable of.
Well, the tape in a Turing machine is infinite, like in the definition.
Yes.
And each of the individual pieces of the tape contains a 0 or 1.
Each individual component of the tape has a 0 or 1, and in a theoretical Turing machine, the tape is infinite. Great, that's an important detail.
It can write to the tape?
It can write to the tape. So there's actually two actions that a Turing machine is capable of. Move left and right, and write to the tape, or erase the 0 or 1 that's there and replace it with a 0 or 1. So we've got inputs and outputs. One last thing we're missing. Initial state. So what do you mean by state?
Like there's sometimes information on the tape already.
There's information on the tape already. So you're talking about the state of the tape.
It can halt
It can halt, so it can stop doing things. Yeah.
and it can accept.
Can accept an instruction. Is that what do you mean by accept?
It'll like halt it'll halt in an accept state or reject state.
Okay, yeah. There's accept and reject states. You're right. Not that detail. We've got input, output. I'm fishing for something now.
I'm guessing just like environment where it starts at.
Yeah, initial state, initial conditions. Where do we put the machine relative to the tape?
Tape alphabet.
Tape alphabet, kind of getting there. Zeros or ones. Still fishing. Input, output. One more thing that the Turing machine is capable of, or has.
The head processes the input and then.
It processes the input. Try one more
It
time.
can move between states.
I can move
Internally,
between
yeah.
states. Where are those states?
In the like brain.
In-
I don't know.
Thank you. Inside the machine. So Turing machines have internal state. So I'm a Turing machine. I see 1 on the tape at the moment. I see a 1 on the tape, and I have a certain internal state. So I combine my input with my internal state, and that dictates what I do next. So I'm talking, and your internal state is you're awake. So some of you are writing on pens and paper or tablets. Awesome. That's good. You might have a different internal state, which is you're not quite awake yet. It's 8:30 in the morning. So you're still technically getting the same input. I'm still talking, but you ain't writing, right? Different action because of different internal state. So the key thing I want you to, if you haven't seen a Turing machine before, that I want you to take away from today is this is a machine that's kind of different from all previous machines up until 1936, or at least they were never formalized in this way. A Turing machine is something that sees external information, that's the input, brings it inside and combines it with internal state to do what we now call internal processing. And then it does something. It has a set of possible actions, which for a Turing machine are erase what's currently on the tape and write a new symbol, or move the tape back and forth. Yeah? If you think about a Turing machine, and I kind of gave you an example of this already, that's what we do, right? You're sitting here receiving some input, hopefully from my voice, from the slides. Hopefully, you're combining it with your internal state. You're thinking about what I'm saying and what you're seeing, and then some of you are doing something. Hey, we kind of seem like Turing machines as well. It's obvious. We take stuff in, we cogitate, and we produce stuff as output. It's obvious. That's a very good summary of who we are and what we do. You're going to get tired of hearing me saying this in this class, but thinking about thinking is misleading. It feels to you like that's what you're doing, but I hope that by the end of this course, that way of characterizing us will be thrown into doubt. Maybe that's not quite what we're doing. Maybe we're doing something else. Okay, enough about us. Back to machines. Turing created this hypothetical idea, and then going into the war, and on the other side of the war, people, including Turing, started to make physical versions of a Turing machine. Every smartphone, autonomous vehicle, every laptop, every supercomputer, every computer on the planet is a physical instantiation of a Turing machine. Okay. All right, that's the 1930s. Let's jump ahead. That was 1936. Let's jump ahead another 20 years to 1956. So at this point, people had been thinking about and building actual computers for about 20 years. And again, Turing and others said, wow, we're making these new things called computers. They sometimes seem like they're acting smart, and humans also take input, internally process, and produce output. So could we make a smart computer? Could we make a computer that's almost as smart as a person? Wait a second. Could we make a computer that's as smart as a person? Wait a second. Could we create a computer that's smarter than a person? What do we mean by smart at all? These ideas were in the air for a long time leading up to 1956. But in 1956, a dozen professors got together and said, let's spend the summer of 1956 actually figuring this out once and for all. So what you see here is an excerpt from a proposal those professors wrote in the spring of 1956 that they submitted to the government as a proposal and said, give us some money to hang out at Dartmouth, just down the road from here, for a summer. And if you give us a little bit of money, it should take us about 2 months, and we're 10 men. Of course, this is the 50s, no women, 10 men, we're going to study this thing called artificial intelligence. This was the very first time this word was used. We proposed that us and our buddies are going to spend 2 months at Dartmouth to figure this out. What we're going to do is we're going to proceed on the basis of the following conjecture. We conjecture that every aspect of human learning or any other feature of human intelligence, all the things that humans do, chess, poetry, math, can in principle be so precisely described, we're going to actually come up with a formal definition for intelligence. If we can define intelligence precisely enough, then we can simulate it in a computer. Maybe we can simulate intelligence in a computer. It won't be real intelligence because it'll be simulated. Some members of this 10-man group thought they could go further. We're not just going to simulate it, we're actually going to reproduce it in a machine. But we probably shouldn't say that to the government. That sounds like we're weirdos. Let's just say simulate, that's safer. Better chance of us getting the money to do this. Okay, we're going to make an attempt to find out how to make machines, and now they start to break down intelligence. For them, intelligence is about using language, forming abstractions and concepts, and now solving the kinds of problems that are now reserved for only us humans. And most of these problems, like forming abstractions and concepts, another word for math, we, the 10-man group, were actually really good at this. They were mostly mathematicians. What a surprise, they thought that was the best definition of intelligence. And also, by the way, we'll get these computers to improve themselves. Another feature of intelligence, which wasn't mentioned last class, self-improvement. Seems like another hallmark of intelligence. Okay, we think that a significant advance in all of this can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. They got the money, they hung out together for a summer, they did some math, they did some computer programming. They did not end up creating AGI, artificial general intelligence. Turns out creating intelligent computers is kind of a hard thing to do. You could argue that in just the last few years, we've started to make some real progress in this, but it turns out it's harder than we thought. Thinking about thinking is misleading. It should be pretty easy to sit down and formally define intelligence and then turn that formal definition into a computer program, run it on a computer, and we're done. We've got smart computers. Not so easy. In my opinion, personal opinion, we still have a very long way to go, which is why I teach this class, and I hope that some of you join the effort to try and make autonomous, safe, and useful machines. Okay, here's the attendees. Anybody recognize any of these names? Claude Shannon, the founder of information theory. Some people say we currently live in the information age. What do we mean by information? Turns out there is a formal definition for intelligence, and Shannon was the one that formally defined it. In his master's thesis, by the way. Other names you recognize here. No? Okay. For those that are interested in the history of AI and robotics, I suggest you go look up some of these names. John McCarthy was the organizer. He's the one that actually wrote this proposal. He was the one that invented the term artificial intelligence. Marvin Minsky, there's Marvin down there. He went on to co-found the MIT AI Lab. This is kind of known as Mecca for all things AI. Next time you're in Cambridge, Mass, go by the Stata Center. That's where the MIT AI Lab is. is. It's open. Most of the building is open to the public. It's a beautiful building, great place to visit. Okay, we mentioned Shannon already. Herb Simon was an economist, actually. Kind of interesting. There is a link between economics and AI that has to do with decision making. Some of you may have taken a class here with Professor Skalka. Professor Skalka was Herb Simon's very last PhD student, so a living link with the past. Okay. All right, let's take a pause for a moment. So we're working our way through a history of AI. What is it we're trying to do? Where is it we're trying to go? I keep saying we're trying to create autonomous, safe, and useful machines. Yes, okay, that sounds great, but let's try and get a little bit more specific about how we're trying to do this. There are 10,000 different ways that folks are trying to achieve AGI, or this goal of useful, safe, and autonomous machines. Generally speaking, across all these different efforts, including evolutionary robotics, you can kind of see three sub-goals at work. The first one is to look around us, right? There are arguably 8 or 9 billion intelligent machines on this planet. If you're willing to extend your circle to include other non-human animals, Mother Nature has done a very good job at producing vast numbers of safe, autonomous, and useful, at least to themselves and their kin, machines. How did she do it? Can we just borrow what she did? We're going to see the term bio-inspiration or bio-inspired. It's going to crop up a lot in this class. That's what we mean. Let's try and understand biological intelligence. And as we do, we're probably going to have to distill out the general principles. I mentioned opposable thumbs. There's some very beautiful engineering in our shoulder sockets that allowed our ancestors to throw spears at antelopes. Do we need to build those particular physiological details into a humanoid robot? Maybe yes, maybe no. Turns out it's tricky. What parts of human intelligence, what parts of human physiology and human neurophysiology do we need to preserve and build into machines to get a machine that's intelligent and autonomous and safe? And which parts can we safely abstract away? This is where most of the disagreements in AI and robotics come from. AI researchers say we can throw away the body altogether. We don't even need it. That's just the way that Mother Nature needed to produce intelligent machines. But when we do it in computer code inside a computer, we don't need the body. Roboticists say, you're crazy. Of course we need the body. Now, which aspects of the body? I don't know. So this is tricky, and we're going to see lots and lots of different experiments in this class where people make different design decisions here. And then finally, obviously, we need to take this abstraction, this thing that we've abstracted, and write code that instantiates it, or build a robot body and code that goes into a machine that instantiates those general principles of intelligent behavior. What might be some candidates for general principles of intelligent behavior? What can't we throw away? What do you do? What are you capable of that allows you to survive and learn and self-improve and adapt that we should probably build into machines as well?
A way to receive input?
Input. Whatever it is, there needs to be a way for the machine to receive input. A blind, dumb, and deaf machine is probably going to have a hard time exhibiting intelligent and adaptive behavior. Other things. Give output. You got to act, right? You have to show that you're intelligent rather than just tell. Other candidates. Yes?
Probably a brain to do the processing.
Maybe we need a brain. Okay, there we go. Controversy number one. I don't know that I agree. You might be right. Nobody knows. Brains are obviously important. We have big ones, and we're really smart. Therefore, robots and AI are going to need brains. Maybe yes, maybe no.
We need a way to provide different outputs depending on what the input is.
There needs to be something, I'm going to put these in scare quotes, decision making, right? Depending on what I sense at any given point in time, I might want to do different things.
Predicting inputs and evaluating that with sensor readings could possibly
Okay.
in an efficient model.
predicting future sensory information. So I'm going to flex my bicep, and I predict that I'm going to see a black Sharpie show up in my visual field about 1/10 of a second later. Ah, look, my prediction was correct. Great. Okay, I feel confident that I know what to do in the current situation. So you mentioned prediction. What is it that brains do that some of us feel are very, very important? One of the things they seem to be very good at is predicting, making guesses about things that are going to occur in the future. So one of the things that intelligence seems to need is being able to grapple or reason or think about or plan for the future. So time is tied up somehow with intelligence. Okay, we could keep playing this game all morning, but just to give you a sense, sometimes it's a little tricky to know what to keep and what to throw away. Okay, here's a Lego Mindstorms robot. Some of you may have played with these as kids. Here's a robot that does not necessarily an intelligent behavior, but it's an adaptive behavior. It's called phototaxis, moving towards a light source. The designers of Lego Mindstorms, they threw away most of what we do or what animals do, and we're left with something very, 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 very simple. So there is not a lot of internal processing going on inside this Lego brick, and we'll see exactly what processing is going on inside this brick in about 10 minutes. But just, again, as a visual reminder of this idea, here's a robot that does something reliably, and they've thrown away 99.99999% of the physiological baggage that we all carry around every day. You can get away, in some cases, with relatively little. Okay, let's jump to the 60s. Now we've got computers that are not in every home and office yet, but you now have computers that are in every university, pretty much. And you had a growing number of people that were writing computer code, and you had a growing number of people that were writing code to try and create smart machines. One of them, Joseph Weizenbaum, wrote the ELIZA program, which was a computer psychotherapist. I'm feeling terrible today, Eliza would say. I'm so sorry to hear that. Why are you feeling so terrible today? It turns out that when Weizenbaum released this code, he invited into the university lab hundreds of people that sat at a terminal and were able to talk to Eliza. And some of those people stayed there for hours and hours and hours on end and poured out their hearts to Eliza. Maybe not so surprising to you now when we live in the age of ChatGPT and AI boyfriends and girlfriends, but at that time, it was amazing. Weizenbaum obviously knew what ELIZA was. ELIZA was a very big set of if-then-else statements. I say very big, it wasn't actually that big. ELIZA would take the sentence and parse the sentence, or the if-then-else computer program would look for pronoun, verb, proper noun. I feel terrible. And the else statement, or the then statement would say, if you see that pattern, write out why do you, verb, proper noun. Why do you feel terrible? And tack on a question mark at the end. There were a few hundred of these kinds of templates or frames. And amazingly at that time, that was enough to ensnare and entrap a lot of humans into conversing and pouring out their hearts to this machine. A big eye-opener at the time that, again, it didn't take much to convince people that Eliza is empathetic, Eliza is intelligent, Eliza is sensitive, Eliza cares about me, Eliza is patient. This was amazing at the time. Starting then, at least AI researchers started to realize that humans suffer from an incurable disease called anthropomorphization. We often err on the side of caution. We often attribute human-like properties to things that are not human. We do this with our pets all the time. We now do this with chatbots, but this was very new at the time. Okay. Let's jump actually back to the Turing test. Why are we talking about the Turing test? Because unbeknownst to a lot of folks talking to Eliza, The way that they then described Eliza, empathetic, caring patient, made it sound like Eliza was passing this test that Turing had proposed not that long before. I'm going to leave the sound off in this clip. I'm going to turn off the lights for a moment. For those of you that haven't seen this clip before, we have an interviewer here, and in a moment, an interviewee is going to come in, and this interviewee is a little anxious. There's our interviewee. He gets the sense that he's about to be administered a test. He's a little unsure what this test is. He's a little unsure about what this organization is. He's a little unsure about this interviewer, what exactly is going on. The interviewee on the left here becomes even more anxious and confused when the first question the interviewer asks is something cryptic. It's got something to do with a turtle in the desert. The interviewee is even more confused, asks a few questions about why that question is even being asked. The interviewer seems to be a little bit reluctant to answer, and eventually goes on to another question about the interviewee's mother, to which the interviewee responds, "Let me tell you about my mother." And for those that haven't seen this clip before, I won't spoil it for you. Suffice it to say, things don't go very well for the interviewer. Lights back on. What is this clip from? Please don't leave me hanging.
Blade Runner?
Thank goodness. Okay, I'm not that old yet. Blade Runner, for those of you that haven't seen it or read the short story on which it's based, required homework for tonight. Okay. The Turing test, I don't know that it even needs an explanation these days. Turing's perspective, this idea from the 1950s of the Dartmouth workshop that we need to formally define intelligence, which we can then turn into computer code, Turing became increasingly skeptical that that could even be done. He said, I don't know how to formally define intelligence, but I know it when I see it. So for Turing, the way that we would measure intelligent machines was operational. The machines would have to do something. And for Turing, what that thing would be is convince a human interlocutor, the human that's talking to the thing, trick the human into thinking that they're talking to another human rather than a machine. That's the Turing test. Okay. Typically applies to non-embodied AI technologies like ChatGPT and Claude, not necessarily robots. Turns out for robots, there is a physical Turing test, and we'll get to that a little bit later. Okay, we're just touching on a few concepts that are important in the history of AI. Let's jump ahead again now to the 1980s. I know the text is very small here. I don't expect you to read it. This is the Chinese room argument. Hands up if you've heard the Chinese room argument before. Only a few of you. Okay, all right, here we go. So John Searle, you can see in the bottom left here, was a philosopher, and he had a real problem with the Turing test. He said, I don't like the Turing test as a measure of whether or not a machine is intelligent for the following reason. Searle said, I can construct a thought experiment in which a system, it's not necessarily a machine, but a system passes the Turing test, and this system that I'm about to describe to you obviously is not intelligent and obviously doesn't understand the questions being posed to it. That system for Searle was called the Chinese room. Here we go. As you can see, there's a room. There's a person inside. We'll assume this is a native English speaker who does not speak Mandarin. No Chinese whatsoever. The folks outside the room are native Mandarin speakers. They write some question or prompt, I guess we would say these days. They write a prompt in Mandarin on a piece of paper and then slide it through the slot in the door to the person inside the room who receives this piece of paper. And from this person's perspective, they look at this piece of paper and they see a whole bunch of squiggles on the piece of paper. I think we can all agree at this point that that person does not understand the question. Yes? We're okay? Clearly no understanding at this point. Okay. They turn to this huge dictionary sitting at the back. The dictionary is written in English, which they can understand. And the dictionary, it's kind of an odd dictionary, or it's a lookup table. It says, if you see this squiggle followed by that squiggle followed by that squiggle, get a fresh piece of paper and write this other squiggle and then this other squiggle and then this other squiggle. Sounds kind of a lot like this thing down here. Yeah? Okay. The person inside the room does exactly that. They copy out some new squiggles according to the book on a fresh piece of paper, and they pass the paper back out through the slot. The native Mandarin speaker gets this new piece of paper and reads it and says, what a compelling, beautiful, creative, cogent, well thought out response to the question that I passed into the room. If you were to ask this person, they said, whoever or whatever is inside that room clearly understands Mandarin. They understood what I said. How is this possible? Where did the understanding come in? The person clearly didn't understand the squiggles. It seems ridiculous to say that a book understands anything. It's an inanimate object. It's got no circuitry. It doesn't understand. The room's made up of cement and mortar and bricks and plastic. Those things don't understand. I don't get it. What happened here? What went wrong?
Kind of induces the bias of like the creator of the book or the creator of the chatbot. Like they're the ones making really the decisions. It's not learning it itself.
Okay, so maybe the person who wrote this book understands. Did they understand the question that got passed through the door? That's what this person believes. This person believes that whatever is inside this room understood the question. What you mentioned is maybe the closest we can get. Somebody who understood Mandarin wrote this book, but they didn't understand the question. They're not even here. For all we know, they're long since deceased. Where did the understanding come in? The understanding of the question that was written on the paper to begin with. Did it?
It was projected onto the room by the outside speakers.
It was projected. This person was tricked. They think there was intelligence, or they thought there was understanding. From their perspective, although they don't know it, they're actually projecting understanding, not onto the person inside or the book inside, but the system as a whole. So what do we do with that? The person got tricked. You're all listening to me, and hopefully I'm making sense to you, and hopefully you're understanding what I'm saying. Hopefully you think I'm understanding what I'm saying. I hope that I'm passing the Turing test that you are unconsciously administering to me. Do I understand? The room clearly doesn't, according to Searle, right? It's a trick. According to Searle, we can never make machines that understand. The only thing we can ever do is make machines that don't understand. They're just fancier and fancier versions of this, including, by the way, foundation models and all those fancy AI models that we have now. They don't understand, and they will never understand. They can trick rubes into thinking that they understand, but they don't, and they never will. Are you all okay with that? Yeah? Okay. What's the difference then? Do I understand? Do you understand? I see a shrug.
I think it's like there's a separation between thinking and cognition, where thinking is like a trait that is applied to things, like from our perspective, whereas it's like comprehension. That's what I want to use.
Comprehension. Okay. A good point. So one way, we're not going to solve the Chinese room today. I just want to invite you into the problematics of the Chinese room. One way of grappling with the Chinese room is synonyms. For Searle, he talked about understanding. That was the verb that was important to him. There are maybe different words we could use if we want, and then things become a little bit more comfortable. In my experience of grappling with the Chinese room, even if you choose cogitation or thinking or other terms, it's still problematic. It feels, personally, I feel like, yeah, I don't think the Chinese room understands, but I do. I'm different. You're different. How? Well, I'm not quite sure, actually.
I feel like it's kind of like the idea of like abstraction, like where that room is only able to take those inputs and directly tell you what to do.
Okay.
We're able to take new information and like you're able to respond to us and change your body language or your teaching, like whatever, in order to respond to it, showing like that adaptation to the stimulus or the environment that like you can't necessarily prove that it's doing that if it's just copy pasting what's in the book.
Great point, right? So maybe we do things, the room is limited. The room can't move around. It can't necessarily adapt, right? There's this book that's written in ink. The book's not going to change. So the room is limited in some way that we are not. Thank God. Okay, we're safe. We're not Chinese rooms. We're different. We're better. There's things we can do that the Chinese room can't do. Okay, it's kind of a temporary win, though. Why?
What if instead of a room, it was a car with the window sealed and somebody could pass in instructions to drive somewhere?
Let's put some sensors and motors and wheels and arms and legs and other things onto the room. And now saying, well, there's things we can do that the room doesn't do. That gap becomes narrower. Again, kind of an uncomfortable situation to be in. So if you haven't before, I invite you to think about and grapple with the Chinese room for a little bit. And if you can, try and convince yourself that there are things you can do that the room can't do or will ever be able to do. Tricky to do. I mentioned last time some of the reasons why I like robotics and AI. Another reason I like them is that they're a challenge to us. We are unique. We are on a planet and all these other things revolve around us. Oh, that was not correct. All right, well, we're great and there are all these other animals, but they're different from us. Oh, we're actually related to them? Okay, that's problematic. One of the things science tends to do is militate against hubris, right? There's something that I can do or something that I am that the Chinese room isn't or can't and will never be able to do. That's Searle's position. You may adopt the same position. From my point of view, it's a tenuous position to hold. Again, you don't need to agree with me. You can come to whatever conclusion you want about the Chinese room, but I invite you to think about it. Okay, we're still in the 1980s here. Let's talk about Valentino Breitenberg for a moment. Valentino Breitenberg was a neurophysiologist. He actually studied the physiology of brains, not of human brains, but of the brains of fruit flies. So you've all experienced student housing. You know your roommate leaves out some rotten fruit, and sure enough, you've got fruit flies everywhere. You know how small a fruit fly is, very, very small. Imagine how small the brain of a fruit fly is. If I had some fruit flies with me today and there was a piece of rotting fruit in the back corner of the lecture hall and I opened up the vial, those fruit flies would come out and they would fly, not exactly, but more or less they'd make a beeline for the rotten fruit. How do they do this? In the 1970s, there were a lot of neurophysiologists arguing that brains were doing differentiable calculus in their heads. They were solving fluid dynamics equations to figure out how to ride the microcurrents of air in the room to get to the fruit. Breitenberg, at that time, when he was younger, he was at the bench actually dissecting fruit fly brains and started to think about or started to wonder, how could there be differentiable calculus being done inside something this small? Doesn't seem right. I'm not sure that that's the case. Breitenberg started to realize that there might actually be simpler explanations for the ways that, for example, fruit flies are able to triangulate and approach rotting fruit. And he eventually encapsulated all of his ideas in this fun book called Vehicles. Again, if you've never come across this book, I highly recommend it. It's not very technical, it's very short, and it's written like a fairy tale. In chapter 1, Breitenberg describes a very simple vehicle. He used the word vehicle to try and imply that this thing that he was describing could be a robot, could be an organism, could be anything else. Obviously, for us, a vehicle implies technology. But let's imagine this thing is maybe technological, maybe biological. Whatever it is, it has a sensor or a sense organ on the front that detects temperature. The warmer that sensor is, the more strongly it fires. The colder that sensor is, the less active that sensor is. Imagine that temperature sensor or temperature sense organ is attached by a wire or a nerve fiber to either a wheel or a tail on the back. Input, internal processing, output. So far, so good? Okay. In this fairy tale, in chapter 1 of this fairy tale, Bratenberg says, imagine now what you would think if you saw such a vehicle, a robot/organism, swimming around in a pond. It's restless, you would say, and does not like warm water. But it's quite stupid since it's not able to turn back to the nice cold spot it overshot in its restlessness. Let's think about this for a moment. So if the sensor is cold, that means the sensor is firing less strongly. It's sending a weaker signal along the wire or nerve fiber that's causing the wheel to turn more slowly or the tail to swish back and forth more slowly, which means the robot or organism is going to slow down in cold temperatures and slow down but maybe not stop. So once it overshoots that cold spot, it's going to speed up again and go faster. Anyway, if you saw such a tiny thing swimming around in a pond, you'd say it's alive, since you've never seen a particle of dead matter move around quite like that. Would you say that? Is this thing restless? Is it stupid? Does it regret that it overshot this nice cold spot that it likes? Good, accurate language? You all okay with that? I see some nods, I see some shaking of heads. Let's keep going. That's chapter 1. In chapter 2, Bratenberg introduces 2 new vehicles, 2A and 2B. Here's 2A, which has the nickname of the aggressor. A little bit more complicated machine. Now we have 2 sensors on the front. They're not temperature sensors anymore, they're light sensors. The more light falls on the sensor, the more strongly that sensor fires. We've got 2 wheels now. We'll assume this vehicle is on land. And it is contralaterally connected. Contra meaning across, lateral meaning the side. Crossing the sides of the animal or the machine, left front sensor attached to the right back wheel, right front sensor attached to the left back wheel. Imagine we now get out a flashlight and we approach this robot from its front left. As you can see in the little cartoon here, in the next moment of time, that vehicle is going to turn a little bit towards the light. Why? Give me a mechanistic explanation. What is it about input, internal processing, and output that produces this left turn?
Well, when the sensor closest to the light gets more light, it'll probably make the motor on the opposite side then fire harder, so it'll then turn towards the light.
That's it, right? So at this instant of time, there's more light falling on the left sensor because it's closer to the light, which means the right wheel turns faster, which means the whole vehicle turns to the left. Everybody see that? Not that hard, right? Okay, we're dissecting our first robot. It's not that bad. We've dipped our toe into the shallow end of the pool. Okay, what happens at the next moment in time? The robot has turned a little bit towards the light. What happens next?
As it's facing it and both sensors kind of get the same, they're both going to like equally move forward with the same signal and drive forward. There's no differential in the sides.
It stops turning and now goes straight because it's turned to face the light, which means both light sensors are receiving the same amount of light, which means both wheels are turning at the same speed and it goes forward. You're running, you might not realize it, you're running a little bit of a simulation in your head now of the robot's environment, the robot, and the robot's internals. This robot is simple enough that you can do this in your head. Okay. It's now moved a little bit straight towards the light. There's one more wrinkle or one more feature of this robot's behavior that we haven't described yet. What happens at the next moment of time?
As it gets closer and closer, it'll speed up because the light's brighter.
Absolutely. We get into a positive feedback loop. There's more light falling on the sensors, means the wheels turn faster, which means the robot accelerates. And if this is not a flashlight, but a naked light bulb, it'll smash into that light bulb and destroy it. The aggressor hates lights with a passion. The Lego Mindstorms robot that we just saw a few moments ago, that's exactly what that Lego robot instantiates, this program. This robot obviously hates light with a passion, right? You're all nodding. Okay, a lot of animists in this class. I like it. Does it? Does it hate? Where is the hate? There are two contralaterally connected sensors and motors. Where's the hate circuit? Tricky. All right, we'll do one more, and then I'll leave the rest of the book for you to read, which is optional. 2B, same thing as vehicle 2A, two light sensors on the front, two wheels on the back, but now we have same ipsilateral connections. It's the only change. We now come at this robot with a flashlight from its front right. What does this robot do? Turns away. There's more light falling on the right sensor, which means the right wheel turns faster than the left wheel, so it turns away from the light. What happens at the next instant of time? It's turned away. Let's assume that the sensors are omnidirectional, so there's still light falling on the sensors, even though the light is now a little bit behind the robot. It's back, the light's around here somewhere. What does the robot do next? I see somebody acting it out. Yes? What does it do? It runs away. Okay, so there's still light falling on the sensor, so it's still moving away. But if I just stay here with my flashlight, what happens? Yep.
Slowly stops.
It'll slowly stop because the further away it moves, there's less light falling on the sensors and it'll slow down. Now what happens? You mentioned it before. If I come at it with a flashlight, it'll move away, and you said run away, and it runs away because it's terrified of the light, right? It fears the light, obviously. Where's the fear? If/when you read vehicles, you'll see all sorts of language like this. This is a very serious scientist, a neurophysiologist, and he's talking about loving vehicles and hating vehicles. Seems crazy. Why would a serious scientist write a book like that? Why would he use such language? What's the point he's trying to make? Yes?
He's asking if animals that we like anthropomorphize actually feel the way we think they feel.
Right. I don't know, right? We don't know. Kind of an uncomfortable truth. Now, obviously, humans love and hate. This we can be 100% certain of. We have it somewhere in here. We love, we hate, we regret, we expect, and so on. This thing obviously doesn't. I get it. Bratenberg's is trying to amuse us, right? He's deliberately using language like love and hate for something that obviously doesn't have it. Then there's all the non-human animals in between that we're not sure of, but we're sure about us, right? We have it. We love and we hate, obviously, because I hope one of you answers, right? You're on trial now.
We define those concepts, so we're like the benchmark for them.
Okay. Yeah, here's the line, right? We're on this side of the line. Everything else, I don't know. Because we're okay to draw the line here because we have what? We have a brain. Therefore, we love and hate. Okay? There's non-human animals that have brains, so I guess we have to draw the line around things that have brains. Okay. You okay now? Love and hate circuits, they're clearly somewhere in here. No problems, obviously. Still okay with that? So everything that doesn't have a brain Doesn't love, doesn't hate, doesn't suffer. We can do whatever we want with things that don't have brains. No problems, right? What evidence do we have that there is a love circuit, a hate circuit in brains? Have we found it? It's clearly not in here. This thing has 2 wires. You have, 10 to the 12 wires. You have 10 to the 12 synapses, mostly in your central nervous system. We got more wires. It's probably in there somewhere.
It kind of reminds me of like the studies where they do with dogs, like when their owners come home and they're like, oh, dogs have the same responses of like dopamine and stuff as
Yep.
when we feel love for someone.
Therefore, great point, right? Look at dogs clearly love their owners. It's obvious from how they behave. This thing obviously behaves as if actually, do I have it on here? I think it's vehicle 3 is the lover. There's another one that does something very much like a dog when its owner comes home. So that definition is kind of problematic, right? If we're going to attribute emotions to things that act as if they have emotions, we have to include Bradenburg vehicles with us. But they clearly don't have it, so now I'm not sure whether we have it. Even with arguably the simplest robot you're going to see in this course, it already becomes problematic for us to claim that we, or things like us that have brains, uniquely have emotions in an internal life. We suffer, these other things don't. I'm not trying to convince you that you're a Bradenburg vehicle. I'm also not trying to convince you that you aren't. Come to your own conclusions. What I want you to take away from this is, again, in the history of AI and neural physiology and robotics, things get tricky pretty quickly. Thinking about thinking is misleading. I love, I hate, this thing clearly doesn't. Tricky. Okay. All right, how are we doing for time? 4 more minutes. All right, 1980s, connectionism. We saw ELIZA. So in the early 1980s, people were writing larger and larger and larger and larger if-then-else statements, and it was getting harder and harder to do it. So some researchers said, let's abandon this if-then-else statement approach altogether, and let's do something that's more bio-inspired. Whatever intelligence is, it's somewhere inside this thing. So what does this thing do? Well, if you look inside, there's a whole bunch of neurons. You have about 10 to the 9 of them. And those neurons are attached together with synapses, and you have about 10 to the 12 of them. A lot of neurons and wires, and they seem to be doing parallel processing. It's not this neuron turns on, then this neuron, then this neuron. There are these sort of flows of information going on from a human's sense organs, from our eyes and ears to our muscles. So let's make an artificial neural network. And because we don't realize it, we're influenced by Cartesian dualism. Brain and mind matter, but body doesn't. We can throw away the body. We can throw away this stuff. And we can also throw away sensors and motors. And we'll just give input to the artificial neural network in the same way that we give a tape to a Turing machine. And we'll just interpret the output. So that was the birth of artificial neural networks. And as you all may know, that brought on an AI winter. People got very excited about these things in the early 1980s, but it turns out that they were problematic. They didn't quite do everything that the neural network researchers promised they would. Why were they promising so much? Because those researchers needed government funding. I also need government funding. I'm guilty of this as well. When you ask the government for money, sometimes you kind of exaggerate and you're a little bit too optimistic. So at that time, neural network researchers were making promises to DARPA, the Defense Advanced Research Project Agency. They were a little optimistic. So the next time they asked for DARPA money, DARPA said, well, wait a second. Last time we gave you money and you promised X, but you only gave us Y. I don't think we're going to give you money anymore. The tap got turned off. Things got very bad for a lot of folks. And it became illegal in academia to even mention the word neural network or brain-inspired. And these neural networks went into hibernation for a long time. A couple of researchers kept working on neural networks with very little funding in Canada, at the University of Toronto, in other places. It's kind of like the mammals hiding in the underbrush from the dinosaurs. They kept working on neural networks. And in early 2000s, suddenly things started to work again for these neural networks. They figured a few things out, and here we are 20 years later after that. We are now enjoying an AI high summer. If you're interested in AI summers and winters, go check out the Wikipedia page on it. We'll pause here for today. You have a second quiz due. Undergrads, you're working on assignment 1. Grads, you're working on assignments 1 and 2. And I will see you all again next Tuesday. Have a good rest of your week.